Thank you so much for coming to listen my talk. Actually, my name is Yungang from ICT. So probably some of you may not know ICT. I just take 1 minute to give a very quick introduction. ICT is actually was founded in 1956. This is the first institute in computing technology area in China. So ICT made many the first in China computer history, such as the first digital computer, the first vector supercomputer, the first SMP server, and the first general purpose CPU, and the first DNA accelerator. So you probably know some companies like Lenovo. Actually, Lenovo was founded by ICT. And also there's another company called Dawning. So this is this company. So actually we have built a series of supercomputers. Now we are building the latest one is called Dawning 7000, will be released the next year. So and also we have many startups. So recently, it's like the Cabricom. This is focused on AI accelerators, founded 2 years ago, but now already a unicorn. So that is a brief introduction of ICT. So back to my today's topic. So actually, I'm going to introduce a kind of basic research on computer architecture. I call it labeled computer architecture. So this is going to bring new interface of new interfaces to convey like high-level information, such as like virtualization, quality of service, and the security to the hardware. So first, let's look at one phenomena, see performance variation in systems. So if we run a program, so let's do a small experiment. If we run like a program on a server for 10 times, so this is the execution, the distribution of the execution time. So the y-axis. So if we calculate the performance variation in these equations, so we can see that the performance variation on a single server is quite small, less than 1%. So, but if we look at, if we run a service on like Google's data center, so to process like 10,000 requests, what will happen? So this is the distribution of the response time. So it seems like it's similar to the last curve. But if we look at the x-axis, this is a log scale. So performance variation on a data center, in a data center is like 10 times. So why it happens? So if here is a typical Google server, so we can see that sharing, a lot of sharing on a server. So many services, application level services and system level services, they run on a single server. So, but sharing is okay, but they are unmanaged sharing. So let's see the picture on the right side. This is if we run one application to read 4 kilobytes data from DRAM, so one application, if we run like millions of times, so then seems like a kind of determined the latency. But if we run like 4 applications, such applications together, so the access latency will be there some like tail latency here. So this is very typical in our systems, not only for like DRAM. So actually, unmanaged sharing is everywhere in our systems, like among like SMT, among like last level cache, DRAM, and networking, etc. So how to deal with that? So actually, we know Google, for example, I take Google as an example. So actually, over the past 10 years, so Google has devoted a lot of efforts in software stack optimization, such as like a Borg, like Linux container C group were first used in Google data centers. But today, they still has to suffer the long tail latency issue. So which means most of the requests can, for example, in this picture, most of the requests can be finished in like 60 milliseconds, but some of them have to like suffer from more than like even 2 seconds, 30 times more than normal one. So there's a trade-off between the utilization and the user experience. Here is a case for memory cache D. So if, for example, the utilization is 30%, so that's okay. So the tail latency is only about like 190 microseconds. But if we improve utilization to 70%, so the 99% tail latency increased by 10 times. So that is terrible for user experience. So how to deal with that? So what's the impact of such phenomena on today's data center and cloud environment? So we know that today is most of application accessed by mobile phone, smartphone. So since those performance variation on a single server can cause significant variable end-to-end latency. Here is just a profiling data from Microsoft. So we can see most of end-to-end latency is more than like 2 seconds. So not only on the data center environment, but also for like real-time systems. So this kind of performance variation or unmanaged sharing is also serious. So for example, like as far as I know, some like aircraft, they have to leave one active core and to turn off other cores to guarantee real-timeness. And even on smartphones, so since there are a lot of IP blocks like ARM's bigger core, little core, GPU, and DSP and NPUs, a lot of IP blocks, they share system bus, they share DRAM controller. And so inside the SoC, there are also a lot of contentions and so that to affect the real-timeness or the user's experience. So this is kind of a fundamental challenge on our computer architecture. So then we know that Google actually already realized that several years ago, so they claimed that, advocate that more hardware support needed to solve this problem. Yes, this is the very important direction. So we know that Intel's RDT technology tried to solve this problem. And also ARM is catching. Yeah, ARM's NPAM is, I think this is very timely to address, to tackle this problem. So, but for academia, actually, we have realized this problem since many years ago. So as we see, so this is actually the interface problem. So today's interface mostly rely on instruction set and virtual memory. So, but they cannot convey like quality of service, security information to the hardware. So this white paper was released in 2012. So see, new high-level interfaces are required to solve this problem. So actually, during that time, like during 2010 to 2012, I was in Princeton working on PASIC, and so this is my probably doing meditation. So not for that problem, at that time I was still thinking about PASIC, but yeah, actually Princeton is a good place. It is a very important place for SDN research. So there are many professors, they working on SDN. And for example, the frenetic programming language, and now evolved to be P4. So there are many SDN projects in Princeton. So, and we often talked about SDN. So as a computer architecture, I was thinking, what can we learn from SDN? So what kind of concepts or knowledge we can get from the SDN? So I was thinking about that part since 2012. So, and from architecture, as a computer architect, so this is my view of networking or the SDN. Actually, this is I see this is a kind of a labeled network. So first, each packet has a label. So like MPLs, this kind of label. And then the label is correlated with like a user's demand. And third is the label actually is propagated in the whole network. And then the networking devices like switch routers, they can do differential services based on labels. SDN actually further provides programmability. So that is my view of networking or SDN. So then I compare this networking with our computer architecture. So I found, whoa, so probably we can reconstruct a computer to be an SDN network. Yeah, so because today's computer can be viewed as a network. So actually, the hardware components, they communicate with each other through packets, like PCIe packets. This is a typical PCIe packet. And like a network on-chip packet and QPI packets. So if we do DMA, so actually the packet is going through the system data path. And as for example, there's a network on-chip communication or traffic. So then we can reconstruct computer to be an SDN network. So then we proposed the labeled von Neumann architecture. So it also has 4 steps. First is we attach a tag in each memory request or IO request. Second is, so the label is correlated with a high-level entity like a virtual machine, process, threads, even variable address space. So then the label is propagated in the whole machine. And finally, so we add programmable label control logic. So the control logic is able to provide different services based on label, like label index rules, just like a firewall rules in networking. So this is the general idea of the labeled von Neumann architecture. We call it LvNA. So actually, labeling is not new. So if we look back like 40 years ago, so at that time there was a tagged architecture. Yeah, so try to replace von Neumann architecture. So yes, here there are 3 principles. One is all data elements are assigned with a type tag. So the type is, but the type is quite complicated. Actually, this is a high-level language type. So, and second is all tags are stored in memory, and then the tag will be triggered. The tag will trigger traps or interrupts to process how to deal with tag. So this is idea is quite nice, but it's too complicated to implement. So today we still don't have such kind of tagged architecture machine. So, but we use the different design principles and philosophies. So we try to minimize intrusion to the existing computer architecture. So our design philosophy is first, label should be as simple as possible, so that the label can go across different components. So then ID is a nice choice. Time is also a nice choice. So, but other information, if you want to add more information into label, so some components, they cannot use that information. Second is the labels are stored in requests rather than in memory. So we don't need to to change memory to store such information. So third is control logic resides in data paths rather than memories. And then, So in this way, CPU can be unaware of control logic. We can use other way to program compute logic. So this is so in such design, we don't need to change the pipeline. We only need some modification to the memory hierarchy. So that is the design principles. So based on the general idea, we start to build a prototype. We call it PART. This is a programmable architecture for resource on demand. So first we add labels. We add a label in the machine, and then we add a control logic in some components, and all control logics are connected to form a control plane. And then there is a centralized platform resource manager to abstract all control logic to be files, so that we can use file operations to program the control logics. So, and some details. So then, for example, we add some registers to store labels in each CPU core, and some devices or IO chipsets. And then we assign entity, like for example, in this case is a virtual machine level with labels. When a virtual machine is launched, so it will has a label, and then the label data, the label value will be stored in that register. And all memory requests from that virtual machine will be assigned a label, and the label will be propagated on the whole data path like this. So in this case, and it's a propagation two directions. One direction is like CPU request, another direction is DMA, from devices to memory. So in this case, then the memory controller is able to distinguish the request from which virtual machine or which process, even which threads. So, we add a control logic here. So in our prototype, we add a control logic into three components. It's a last level cache, memory controller, and IO chipset. And also there are some register here. And, but how to design control logic? This is a very challenge. We made some attempts. So first time is we tried to use a microcontroller unit-based control logic. So for example, we design a specific micro MCU to do like a cache replacement, to do memory access encryption, and to do like address mapping for virtualization. So this is very flexible, since we can add arbitrary functionalities into control logic. So, but it's too kind of complicated. So, and the performance the frequency cannot go very high. So then we choose table-based control logic. So this is this is control logic. So there's a template, control logic template. On control logic here, there are three tables and one programming interface and an interrupt line for closed loop controlling. So then the control logic can be integrated into cache controller and be integrated into memory controller easily. So this is currently we choose this design. And the platform resource manager, it connects all control logic to form a control plane. And here it runs a Linux-based firmware to provide an interface to program this control logic, but also it can monitor and get data, monitoring data and interrupts from control logics. So this is the general design of the part. And next is we start to implement the idea. So, but it takes so many time. So since we first built the simulator, and then we built two versions of FPGA prototype. Now we are building chip. So, but here I have to mention RISC-V. So, yeah, we choose when we want to build the prototype on FPGA and want to tape out. So, but finally, we also see how ARM is suitable in the, like OpenSPARC T1 and some other CPU designs. But finally, RISC-V is quite a good platform for research. So then we implemented the labeled RISC-V. This is currently it is 4-core, but it's scalable. So has like a 16-way L2 cache. It's 2 megabytes and DRAM controller, Giga Ethernet. So it can run on different FPGAs. And then we also build a box of FPGA to form a cluster we call FlameCluster. This cluster, each node is a labeled RISC-V to run Linux. It can run like serve file systems, and also can run user-level TCP/IP stack to serve some applications. So it's kind of similar to Berkeley's file sim, yeah. But we have labels. This is different. But anyway, it's they are more flexible since their platform is on the Amazon F1 FPGA cloud. We only have FPGA box, but now we already serve research of many universities in China, like Tsinghua, Peking University, and Tianjin University in China. They remotely log in the FlameCluster to do their research. And so here are some demos of the prototype. This is try to see how to use label to do like a virtualization. So here we can see that actually we put some functionality of hypervisor into control logic. Sorry, this is a Chinese character. So this is traditional computer system. So we have a hardware and we have a hypervisor and then virtualizer to several partition, and each partition can run operating system separately. So, but here with the label mechanism, so we can add put some functionality into control logic. So then on the hardware level, all resources are be partitioned. So then it can run Linux, run different operating system separate directly on these sub-partitions. So even moreover, this red line can move left or move right, so to dynamically adjust the resources. So based on label, we can also, it is very easy to do performance isolation, such as cache partitioning, like memory bandwidth control. So it's since all label-based, so we can distinguish memory requests or IO cache requests based on label. Here is a video. So we put Linux to use all resources, and then we run Redis server on the partition 1. Okay, so memory bandwidth goes up, or cache, last level cache are used by Redis. So currently the tail latency is only like 60 milliseconds on our FPGA platform. And then we run Linux on other 3 partitions. So and each partition run MD5 sort word counters separately. So okay, wow. So you can see that the tail latency, the night tail latency goes up. So we use cache-based, we use cache partitioning to allocate 90% of last level cache to Redis. So okay, almost approaching 90%. But seems like the tail latency doesn't change. You can see that. So this is because the memory bandwidth, the other 3 applications, they use a lot of memory bandwidth. So then we do memory bandwidth control to set up 90% of memory bandwidth to Redis, and then, okay, goes the tail latency revert to 60% as original. So sent to my student to produce the video. So actually, this is just here is some data of the experiments. So, but to form this kind of, if we enable the mechanism, we can achieve almost the same tail latency as original. So, but we have to manually choose policies. This is quite a challenge. So can we do automatically? So then, actually, is it possible? So once we can get a last level cache hit rate curve, then we can find a sweet point. So at that point, we can only allocate that much last level cache to the application, so it's enough, and then we can save some last level cache capacity. So here is one case, our preliminary currently results. So this is for bzip2. So here the green curve actually is how many last level cache we dynamically allocate last level cache to bzip2. And without this automatically last level cache management technology, so this is the blue curve. But with this technology, so the cache capacity is saved by 30%, but the hit rate is still almost the same as the original. So we can, with the label mechanism, it is easy for us to identify how much resources should be allocated to one specific application. Okay, so yeah, we are taping out the labeled RISC-V. It's with the TSMC 40 nanometer technology. The chip will be back next year. So, so it's very easy to change. We added a register here. This is labeled register. We add a control logic at level 2 cache. And we can add a control logic at a DRAM controller. So this is, we connect all control logic to form a control plane. This is the PRM. It's a very easy design. So even for adding labels with chisel, only 10 lines of code. So yeah, there's some extension with the labeled computer architecture. For example, Sally McKee or some other group, they are use label to do security. So things use label to do differential encryption or decryption. And we can also do a fine-grained labeling. So at process level or container level, even address space level. So this all memory request to this address space will be assigned a label. And so I'd like to introduce one work presented in this year ISCA. They call it expressive memory. So they found a labeled computer architecture is very good for them to implement the expressive memory. So and we can sometimes we can enhance programming model so to allow express QoS timing or security information at the programming level. So some more information we have a tutorial at ISCA and this year Micro. So yeah, to conclude is actually we proposed the LvNA. This is actually the kind of concept of software-defined architecture, and the labeled RISC-V is implementation. So finally, I just want to share my experience of a building system. Actually, building system is really fun, especially for the system that will fail and the systems that real work. So to build our prototype without my students' efforts, it won't happen. So I want to thank all my group and thank all the videos here. Thank you.
Okay, thank you very much for that. Do we have any questions from the audience? Go on. I was going to say, Kelly, thank you. will be passing the microphone around.
Nick Dutt from UCI. Thank you for a very nice talk. You mentioned that there's a minimal number of labels that you want to keep.
Minimum what? Sorry.
Labels.
Okay, yeah.
You said, for example, tag and time were two important items. So I'm wondering for the timing abstraction, since you're going across the stack, from the very small granularity all the way up, how do you address timestamping?
Yep.
And especially in distributed systems, that's a huge issue. So can you address, give some insight into how you're going to think about addressing time?
Yes, this is a very good question. So his question is about how to add timing into label. So current design, we didn't add time yet, but there's one work, Pratt at UC Berkeley. So this is, they added timing into to allow like in the computer architecture level. So actually we try to, I have one student, he is going to working on this to add time information, especially time step to go through. So this is doable. So just like the time step on the network, so we can use time step to measure like MTT, to measure RTT. So it's we have a paper about we call it memory RTT, MRTT, to measure memory to measure memory request, the RTT of memory request. It's doable. So, but currently we have only simulation data, not on that FPGA platform yet.
Any?
Simon Moore, University of Cambridge. Great talk. I was just interested to know how you allocate labels. I can see if it's sort of process-based, that's fine, but I'm just wondering how you, particularly in a finer grained system, how you allocate labels and the size of the label and the sort of integrity of that label.
Yeah, so your question about like, how to allocate the label, how to manage the label.
Yeah,
so,
and also just how big they are as well.
Yeah, so the label actually can be managed at different level. For example, at the virtual machine level, if we want to assign a label to a virtual machine, then the label will be managed at like the data center administrator. He will assign a label to a virtual machine or to a container once a job is submitted to the data center manager. So they will create a container for that job, and then meanwhile a label will be created to attach that virtual machine that container. So this is at a container virtual machine level, and it's also doable for like address space level. So at that level should be operating system should be involved. So I think this is there are still many open problem here, but we have tried like a virtual machine level and a container level. Yeah, at a container level, we already need to modify operating system kernel.
Any other questions? Oh, okay, it's one in front and one in Greg. Okay, that's.
It's on your side. Where'd it go?
Hi, Greg Urich from ARM. The demo that you showed in the video, that was running on a core that was implemented at 100 megahertz. Did I see that correctly?
You mean 100 megahertz? Yeah.
Given that the end applications, the cores typically run in a few gigahertz, how might you expect your results to change when you implement a core at those speeds, given that the memory speeds will not change?
You mean how many watts? Sorry.
If you attempt this demo with a core running in the gigahertz range, how might the results change? Do you?
Okay. Yeah. So here is since the CPU core is 1 100 megahertz, and we actually we turn down DRAM frequency. So I think if the CPU runs at like 2 gigahertz, the memory should be should face more pressure, and probably will sometimes the kind of control is more important. Yeah.
Okay, I think this is an easy question. When you added the labeling to the processors that you used in the demo, how much die area increase did you see?
Oh yeah, so this is a very good question. So I didn't put the area overhead here. So actually we have measured this on FPGA. So on the FPGA, the control logic the accounts for about like 3% for cache, DRAM, and the CPU. So, but here is since the cache is we only have 2 megabytes cache, and the DRAM controller is also kind of not that complicated. So I think if for like a commercial or productive DRAM controller, well, the L overhead probably will reduce, yeah, further reduced.
But how big of a table size was the 3%?
The question, please.
Oh.
So it was just a follow-up to the previous question
Okay,
in
yeah.
a way, right? So you 3% overhead, but for what? You had like the
control
table size
logic, yeah, the
for-
table, yeah. So
Yeah.
it's, the table is actually the table size is this is a very important parameters to. So we can since the table we don't have the table now is only we have on that measurement is 8 bits. So the table is 260 yeah. 66. So actually, we talked to some like companies or users, potential users like Alibaba. They said, okay, you can just give me 1 bit or 2 labels. So one is for online service, so one is for batch workloads. So that is enough for them. But so actually probably we don't need that much labels.
Any other questions in the audience? Okay. All right.
Stuart Barnes from ARM. So you said that the supervisor could set the constraints for the container. Are there any considerations you've had there of if you limit the microarchitectural resources for a particular container, does that assist people in side channel analysis within that container?
You mean side channel?
Yeah, so if you just restrained the
Yeah.
container to one way in the cache, would that allow you to probe into it? And
Yeah,
get some more
so this
shadows
is,
from
so the question is this will be useful for like to protect a side channel attack or what?
I guess either way. I guess for a container that would like some guarantees of I need enough resources to make it hard,
Yeah.
could you get pushed into an area where you're not? Can you detect that within the process and kind of refuse to operate? Or
Yeah, I think so. So my understanding is that labeling is actually this is since we can use this way to allocate enough resources for one one partition. So yes, but sometimes it's if we assign label. Well, I mean some shared resources we have to if we want to like protect. From like a side channel attack, some shared resources, we needed to add a control logic for them, like some buffers, queues. So once we add a control logic for those components, I think it is will be very helpful for like prevent side channel attack and to improve security. Yeah.
Thank you.
Okay. Well, thank you very much for that, and let us thank our speaker again.
Thank you.
Thank you very much.